If you look up at the night sky and see darkness, do not be too quick to think of it as empty space. You may be looking at one of the most mysterious places in the universe. The strange thing is, that dark region is not as silent as we imagine. It may still contain ancient light, invisible matter, thin gas, high-energy particles, and quiet traces of the universe's origin. Welcome to Drift into Quiet Knowing. Tonight, we will explore a very deep question. Why is the darkness in the universe not completely empty? When we look up at the sky, the human eye only sees a few bright stars and a vast amount of black space, but our eyes can detect only a tiny part of light. The universe also emits radio waves, microwaves, infrared light, ultraviolet light, X-rays, gamma rays, and even signals that are not light at all, such as neutrinos, cosmic rays, and gravitational waves. So, a region of the sky that appears completely dark may still contain the cosmic microwave background radiation, the ancient light left over from the time when the universe was very young. It has travelled across billions of years, stretched by the expansion of space, cooled down and faded until the human eye can no longer see it. But it is still there, like a distant echo from the dawn of the cosmos. Within that darkness, there is also dark matter, something that does not shine and does not appear the way stars do. Yet its gravity still shapes how galaxies rotate, how galaxy clusters hold together, and how light bends as it moves through space. Just as we cannot see the wind but can see ripples on the surface of a lake, astronomers cannot see dark matter directly, but they can see its traces in the enormous structure of the universe. Even the space between galaxies is not absolute nothingness. There is extremely thin gas, hot plasma, wandering particles, and physical fields that quietly continue to exist. Darkness is not the empty part of the universe. It is the place that stores the first light in visible matter, silent energy, and the deepest clues about the history of everything. So, relax a little, let your mind slow down, and step with me into the black space between the stars. Not to search for emptiness, but to listen to what the universe is hiding in silence. Now let us begin with what seems to be the simplest idea. When we see darkness in the universe, it does not mean there is truly nothing there. It only means the human eye is not receiving enough visible light from that region of space. This is the first point we need to hold on to, because if we misunderstand it, we can easily look at the night sky as one enormous empty space. But in science, darkness is not proof of nothingness. Darkness is often only a sign that our senses have reached their limits. Imagine you're standing under a very clear night sky. There are no city lights, no clouds, and no thin haze blocking your view. You look up and see a few bright stars, a few dimmer points of light, perhaps the faint band of the Milky Way, and everything else is deep black. Human instinct may tell you that those black regions are places where nothing important exists, but an astronomer would not jump to that conclusion. An astronomer would ask a different question. Is that region dark to the human eye, or is it dark to every scientific way of observing? The human eye is a wonderful organ, but it is not a broad enough instrument to read the entire universe. We only see a very small part of the electromagnetic spectrum, which is the vast family of light. That small part is called visible light. It lets us see the blue of the ocean, the yellow glow of a candle, the white light of the moon, and the red colour of a star cooler than the sun. But beyond that tiny portion of light, the universe has many other ways to send signals. There are radio waves, microwaves, infrared light, ultraviolet light, X-ray light, and gamma rays. Each type of light carries a different story about temperature, energy, dust, gas, magnetic fields, star formation, stellar explosions, black holes, distant galaxies, and even the early universe. So, a region of the sky that looks dark to the human eye may not be dark to an infrared telescope. It may not be dark to a radio telescope, an X-ray telescope, or a microwave detector either. An object may not give off much visible light, yet it may appear very clearly in infrared. A region of gas may not create familiar colours, but it may emit X-ray light because it is extremely hot. A layer of radiation may be too cold and too faint for the human eye to see, yet it can still cover the entire sky in the form of microwaves. What we call darkness is, in many cases, only an incomplete translation of reality. An easy example is cosmic dust. In images taken with visible light, dust can create black regions like ink stains against a background of stars. It blocks the light behind it, making us think there is an empty space. But those dark regions are often not empty. They may be cold molecular clouds, filled with gas, dust, and matter that is preparing for the birth of new stars. Visible light is blocked, but infrared light can often pass through dust more effectively. By observing in infrared, astronomers can look deep into those dark regions and discover young stars still lying inside their dusty cocoons. This completely changes how we feel about darkness. A black region is no longer simply a place where light is missing. It may be a place where light is hidden. It may be a place where a physical process is unfolding very slowly, very quietly, and very hard to see. Inside a dark cloud, gravity may be pulling gas and dust together. Denser regions begin to collapse. The temperature and pressure inside gradually rise. After a very long time, a star may be born. In other words, some places look dark not because they are dead, but because they are preparing to create light. Another example can be found in galaxy clusters. When we look in visible light, we may only see galaxies as bright islands scattered through the darkness. But between galaxies in a large cluster, there is often extremely hot and extremely thin gas. This gas is not like a cloud the human eye can see. It can reach millions or tens of millions of degrees, and at such temperatures, it emits X-ray light. If we only look with our eyes, or with optical telescopes, the space between galaxies may seem almost empty. But when we observe it with the X-ray telescopes, that empty-looking space appears as a vast ocean of hot gas. Let us pause with this image. To the human eye, the space between two galaxies may seem like nothing but darkness. But in reality, that place may contain an enormous amount of ordinary matter. It is simply too hot, too thin, and glowing in a kind of light our eyes cannot see. This reminds us that the universe does not have to appear in familiar colours in order to exist. Something may not look as beautiful as a nebula in an optical image, may not shine like a star, and may not form an easy shape for us to recognise, yet it still has temperature, mass, pressure, and history. Darkness, therefore, is not always an absence. Sometimes it is a presence too subtle for human senses. Even the night sky is not truly absolute black if we look at it in microwaves. Across space, there is a very faint, very cold layer of radiation that seems to come from almost every direction. This is the cosmic microwave background, the ancient light left over from when the universe was still very young. When the universe became cool enough for light to travel freely through space, that layer of light began its journey. Since then, space has continued to expand, stretching the wavelengths of that light. Light that once belonged to a hotter universe has become much colder microwave radiation. The human eye cannot see it, but scientific instruments can measure it. This is truly profound. Because when you look up at a black region of the sky, that region still sits against a background of ancient light. That light does not sparkle. It does not have the shape of a star. It does not make a strong impression on the human eye, but it is one of the most important pieces of evidence that helps science understand the early universe. It is like a faint echo from the dawn of the cosmos. And so, darkness does not only contain objects from the present, it also contains memories of the distant past. If the human eye could see microwaves, the night sky would no longer be an absolute black curtain. It would have a very faint background glow, almost even in every direction, with extremely tiny fluctuations. Those fluctuations carry information about how matter was distributed in the young universe, and later, slightly denser regions could grow into galaxies, galaxy clusters, and the vast cosmic web. So, inside the darkness we see with the naked eye, an ancient map is hidden. Not a map of nearby stars, but a map of the universe when it was still young. From here, we begin to understand why modern astronomy is not simply the act of magnifying the sky with telescopes. It is the act of learning how to see with many different kinds of light. Each wavelength opens a door. Visible light shows us stars, nebulae, and galaxies in a way that feels close to human perception. Infrared reveals regions of cold dust, hidden young stars, and light from very distant galaxies that has been stretched by the expansion of space. Radio waves help us recognize hydrogen gas, magnetic fields, pulsars, and many processes that are not obvious to the naked eye. X-ray light takes us to fiercely hot regions, where gas has been heated to extreme temperatures. Gamma rays tell us about the most powerful energetic events. Microwaves carry us back to traces of the early universe. It is the same sky, but each kind of a light gives us a different universe. This does not make the universe more confusing, it makes the universe more real. Reality is not limited by what the human eye can see. Our eyes evolved on the surface of Earth, under the light of the sun, to recognize trees, water, fire, stone, faces, and movement around us. The human eye was not made to see X-ray light from hot gas in galaxy clusters. It was not made to see microwave radiation left over from the early universe. It was not made to hear radio waves from pulsars, or to look deep through cosmic dust using infrared light. So, when the human eye looks up and sees darkness, that is not the final verdict on the universe. It is only the natural limit of a living creature on a small planet. But the most beautiful thing is that humans did not stop at that limit. Science has helped us create new senses. Radio telescopes are like giant ears listening to long waves from space. Infrared telescopes are like eyes that can sense regions hidden by dust and colder sources of light. X-ray telescopes show us regions where high energy and extreme temperatures are at work. Microwave detectors let us touch the oldest light we can still observe. Each tool opens another layer of darkness, and each layer, once opened, shows that places we thought were silent still contain signals. A very clear case is the centre of the Milky Way. In visible light, the central region of our galaxy is strongly blocked by dust between the stars. If we relied only on the human eye and optical light, it would be difficult to look deep into that place. But through infrared and radio waves, astronomers can see through part of that veil. As a result, they have observed the motion of stars near the centre and realised that there is an extremely massive object there, the supermassive black hole called Sagittarius, a star. Here, the darkness is not there because the galactic centre contains nothing. On the contrary, it is one of the most important regions of the Milky Way. It is dark to the human eye because dust blocks visible light, while the truth lies in other wavelengths. Very distant galaxies teach us the same lesson. The universe is expanding, and when light travels through expanding space, its wavelength is stretched. Light that once belonged to the ultraviolet or visible range can reach us as infrared after billions of years of travel. So, an ancient galaxy may look very faint or almost disappear in visible light, not because it does not shine, but because its light has shifted into another part of the electromagnetic spectrum. The darkness here is the result of time, distance, and the expansion of space. The universe has not disappeared. It has only changed the way it sends signals to us. This is why infrared telescopes play a special role in observing the distant universe. They help us see sources of light whose original light has been stretched. They also help us see through part of the dust where stars are forming. A region of the sky that looks dim in an optical image may become rich with information in an infrared image. A tiny black point may hide a distant galaxy, a young star, cold dust, or a structure we previously did not have the tools to recognize. Every time observing technology advances, darkness shrinks a little, not because the universe becomes brighter, but because we learn how to see better. So when we say the darkness of the universe is not completely empty, we're not only saying something poetic, we are saying something very specific in observational science. Not seeing visible light does not mean there is no matter. Not seeing a star does not mean there is no gas. Not seeing colour does not mean there is no temperature. Not seeing shape does not mean there is no structure. A region of space can be dark in ordinary images but bright in X-ray light. It can be dark to the human eye but still contain microwave radiation. It can seem empty in one wavelength but be full of data in another. The absence of one type of signal is not the absence of reality. This also explains why astronomers often combine many kinds of observations to understand the same object. A nebula may be viewed in visible light to reveal its overall shape. Infrared can show where dust and young stars are hidden inside. Radio waves can show how cold gas is distributed. X-ray light can reveal whether very hot gas or a powerful source of energy is active there. When those layers are combined, the picture becomes more complete. If we only look with one kind of light, we are like someone listening to a symphony but hearing only one instrument. The universe is not as simple as a single note. It is many layers of signals stacked on top of one another. The more we understand this, the more we see that darkness in the universe has a beauty of its own. It is not as brilliant as a blue-white star, not as splendid as a glowing nebula, and not as violent as a stellar explosion. But it quietly holds what is not easy to see. In darkness, there is dust hiding newborn stars. In darkness, there is hot gas between galaxies. In darkness, there is the cosmic microwave background. In darkness, there is light from distant galaxies stretched into infrared. In darkness, there are questions the human eye cannot answer on its own. And for that reason, darkness becomes an essential part of cosmic science. We could say that darkness is where science begins to learn humility. Because every time humans think they have seen everything, the universe shows that there is another layer. Before telescopes, the sky only had the stars visible to the naked eye. With optical telescopes, countless dim stars and nebulae appeared. With astrophotography, sources of light too faint for the human eye began to be recorded. With radio telescopes, the sky suddenly gained a new voice. With space telescopes, regions of light blocked by Earth's atmosphere were opened. Darkness has never disappeared in the history of science. It has been reinterpreted again and again. But we also need to be careful. Not every dark region contains the same kind of matter or the same process. Some places are dark because they truly have few bright stars. Some are dark because dust is blocking the view. Some are dark because the source of light is too far away and too faint. Some are dark because the light has shifted into another wavelength. Some are dark because they emit a kind of radiation the human eye cannot see. Science does not turn every darkness into a mystery. Science asks case by case. What wavelength are we observing in? How sensitive is the instrument? Is there something blocking the source? Are there signs of absorption? Is there radiation in another band? And do gravity or motion data suggest anything more? That carefulness is what makes the story trustworthy. If you look at a black region between two stars, that region may truly contain few bright objects. But it may also contain very thin gas that only spectroscopy can detect. It may lie against the background of ancient microwave radiation. Behind it, there may be a galaxy so distant that its light has shifted into infrared. There may be dust in front of it absorbing visible light. There may be high-energy particles passing through it that the human eye could never recognize. A small dark patch, when observed with many tools, can turn into a vast laboratory of matter, light, and time. Perhaps this is the most beautiful way to understand the night sky. When we look up, we are not only looking at what is bright, we are also looking at what our senses have not yet decoded. The stars are the easier part of the story to see. Darkness is the part that asks for more patience. It asks us to use telescopes, detectors, spectrometers, satellites, physical models, and intellectual humility. It reminds us that the universe was not built to fit the human eye. But through science, humans can expand that eye little by little, across many generations. And when the eyes of science expand, darkness is no longer a cold, empty space. It becomes another language of the universe. It speaks through infrared light from hidden young stars. It speaks through X-ray light from hot gas in galaxy clusters. It speaks through microwaves from the distant beginning. It speaks through radio waves from gas and unusual energy sources. It speaks through the fading of light as dust absorbs it. It speaks through redshift as space stretches light. All of these signals repeat one message. The darkness seen by the human eye is not the final nature of the universe. So, at the first layer of this journey, we need to change how we understand the word dark. Dark does not necessarily mean nothing is there. Dark may mean the light has the wrong wavelength for the human eye. Dark may mean matter is hiding the source of light behind it. Dark may mean gas is too thin to create a familiar image. Dark may mean ancient light has cooled into microwaves. Dark may mean light from distant galaxies has been stretched into infrared. Dark may mean a region is waiting for the right instrument to be seen. When we understand it this way, we no longer see darkness as an ending. We see it as an invitation. An invitation to observe more carefully, an invitation to ask better questions, an invitation to remember that the universe is larger than the tiny bright region our eyes can recognize. And perhaps that is what makes the night sky feel so quiet and so deep. The bright part gives us a feeling of closeness. The dark part gives us a feeling of infinity. But now, We know that the dark part is not simply empty. It contains more layers of information than its appearance suggests. It is where light may be hidden, stretched, changed into another form, or so faint that only a sensitive instrument can detect it. So, when you imagine the black space between the stars, do not picture it as a room with nothing inside. Picture it as a room where the human eye has not turned on the right kind of light. Inside that room, there may be cold dust, hot gas, ancient microwave light, infrared light from distant galaxies, radio waves from gas, and extremely faint signals passing through. All of it serves the same truth. The darkness of the universe is not completely empty, because darkness is only the limit of how we see, not the limit of what exists. And from that starting point, we can go deeper. If darkness is not simply the lack of visible light, then behind it are even greater layers of secrets. There is a layer of ancient light that has travelled through almost the entire history of the universe. There are forms of matter that do not shine but can still leave traces through gravity. There are gases and thin plasma so nearly invisible that they are still real enough to affect the light passing through them. There are high-energy particles wandering through space, and there is the deeper question of the vacuum, where modern physics does not treat empty space as absolute nothingness. But before we reach those layers, hold on to the first lesson. The darkness we see is not the final nature of the universe. It is only a very limited translation by human senses. When science expands that translation, darkness begins to appear as a depth full of information. After understanding that darkness is first of all the limit of the human eye, we can go one layer deeper. Because there is something very strange. Even when the night sky looks almost completely black, it is not truly silent. If our eyes could see in microwaves, the sky would no longer be an empty black curtain. It would have a very faint, very cold background glow, almost evenly spread in every direction. That light does not come from a single star. It does not come from one lonely galaxy. It is not reflected light from dust or planets either. It is a leftover trace from the time when the universe was still very young. Astronomers call it the cosmic microwave background. This is one of the most beautiful truths in modern cosmology. The darkness we see today still contains ancient light. Not bright light like the sun, not sparkling light like the stars at night, but a kind of light that has been stretched by time and the expansion of space, cooled down and faded, until it became a layer of very cold microwave radiation. It no longer appears to the human eye, but it is still present. It is like a very distant echo of the dawn of the universe, an echo that does not ring through sound, but through temperature, wavelength, and extremely tiny fluctuations across the sky. To understand why that light matters, we need to go very far back, to a time before there were stars, before there were planets, before there were galaxies as we know them today. When the universe was very young, it was hotter, denser, and not transparent the way it is now. Space at that time was filled with hot plasma, made of charged particles such as electrons, protons, and many photons, which are particles of light. But light could not travel freely over long distances. It kept colliding with free electrons and being scattered by them. Imagine standing inside an extremely thick fog. A light may be shining, but the light is scattered everywhere, making it impossible for you to see through. The early universe was similar in a very deep physical sense. It was bright, but it was opaque to its own light. Then the universe continued to expand and cool down. When the temperature dropped low enough, electrons could combine with protons to form neutral atoms, mostly hydrogen. Once many electrons were no longer wandering freely, light was no longer scattered again and again the way it had been before. The cosmic fog began to lift. Space became transparent, and from that moment on, light could travel across incredibly vast distances through the universe. The light released at that time is the origin of the cosmic microwave background that we measure today. The important thing to remember is that the cosmic microwave background is not light from the first stars. It is older than most of the stars we usually think about. It comes from a time before the universe had the clear, bright structures we see today. It is not an object located in one specific place in space. It is light arriving from every direction, because at that time, the entire observable universe was going through the process of becoming transparent. When we look at this radiation, we are not looking at a distant star. We are looking at a very deep layer of the past, a surface in time where light could first travel freely. To picture it, imagine the universe as a gigantic room that was once filled with hot steam. At first, everything is cloudy. Light cannot travel straight from one side to the other. But as the room cools down, the steam settles, the air becomes clearer, and light begins to move through it. The cosmic microwave background is like the first remaining light from the moment the cosmic room became transparent. Of course, this is only an illustration. The actual physics is much more complex. But the main point is clear. The darkness we see now still carries the trace of the moment when the universe stepped out of its early fog. That light has travelled through almost the entire history of the universe. During that journey, space has not stood still. Space has expanded. And when space expands, the wavelength of light is stretched as well. The original light was once much hotter, but after billions of years of being stretched by the expansion of the universe, it has become cold microwave radiation. Today, the corresponding temperature of this radiation is only about minus 454.8 degrees Fahrenheit, or about 2.7 Kelvin, just a little above absolute zero. The human eye cannot see light this cold and this faint, but with the right measuring instruments, it appears as a background layer covering the entire sky. This is exactly what makes darkness so wondrous. A black region of the sky between the stars still has cosmic microwave background radiation passing through it. A stretch of space that seems to contain nothing significant still lies inside that ancient ocean of light. We do not see it because the human eye cannot see microwaves, but not seeing something does not mean it does not exist. To the naked eye, the night sky is like a black sheet of paper, but if we read it in the language of microwaves, that sheet contains a very old, very faint and extremely important layer of writing. It is a record from the time when the universe was still young. What is even more astonishing is that this layer of light is almost uniform in every direction. No matter where we look in the sky, the cosmic microwave background is there. It is not concentrated in one constellation. It doesn't come only from one bright region. It is the common background of the observable universe. That uniformity shows that the early universe was once very smooth and very even on large scales. But it was not perfectly even. Inside that radiation are extremely tiny temperature differences, tiny compared with the average temperature. Those small differences are the key to understanding why the universe today has galaxies, galaxy clusters, and a vast network of matter. Imagine a lake at dawn. From far away, the surface of the lake looks calm and flat. But if you look very closely, you will see tiny ripples. Those ripples do not break the quietness of the lake, but they tell you there is a light breeze, there is motion, and there is a history in the water. The cosmic microwave background is similar. It is almost uniform, but not perfectly flat. The tiny fluctuations in its temperature reflect very small differences in density in the early universe. Wherever matter was slightly denser, gravity could later pull in more material. Over a very long time, those early differences grew larger and helped create the cosmic structures we see today. So, the cosmic microwave background is not just old light, it is a map. Not a map that draws national borders, oceans and mountains, but a map of the tiny temperature fluctuations of the young universe. From that map, scientists can infer many things about the age of the universe, the ingredients of the universe, the curvature of space, the early distribution of matter, and how large structures could have formed. A light so faint that the human eye does not even know it exists has become one of the strongest sources of information about the origin of the universe. This is why we should not treat darkness as the unimportant part. Very often, the darkest part is holding the oldest data. A bright star may be beautiful, but it usually tells the story of itself, its age, temperature, mass, chemical composition, and stage of evolution. The cosmic microwave background, on the other hand, tells the story of the entire observable universe. When it was still very young, it is not dazzling. It does not have a shape that immediately moves us emotionally, but it carries another kind of beauty, the beauty of evidence. It is the fossil light of space. The word fossil here is worth noticing. When we look at a fossil on Earth, we are not seeing a living creature moving in front of us. We are seeing the remaining trace of a time that has passed. A fossilized leaf is no longer green, but it can still tell us about ancient plants. A fossilized skeleton no longer breathes, but it can still tell us about the shape, size, and environment of a creature that is gone. The cosmic microwave background is similar, but on an incomparably larger scale. It is not the early universe alive before our eyes in the ordinary sense. It is the remaining light trace from a very early stage. Through that trace, we can read the past of the entire universe. But to be precise, this radiation does not come from the absolute first moment of the Big Bang. It comes from a later time, when the universe had cooled enough to become transparent to light. Before that, light was constantly scattered inside hot plasma. So, the cosmic microwave background is like the earliest picture that light can send us, not a picture of the absolute first second. This is a very important point to avoid misunderstanding. Science does not say that we are looking directly at the first second of the universe. Science says that we are looking at the oldest light that could freely travel through space and can still be measured today. When we understand that, the night sky becomes deeper. Every direction we look is not only a direction in space, but also a direction in time. Light from the moon takes more than 1 second to reach our eyes. Light from the sun takes more than 8 minutes. Light from nearby stars can take many years. Light from distant galaxies can take millions or billions of years. And the cosmic microwave background takes us to a very distant observational wall in the past, where the universe had just become transparent. When we say darkness contains memory, this is not a vague image. It is a physical truth. Light takes time to travel through space, and ancient light carries ancient information. There is something very quiet in this thought. While you look into the black space between the stars, the cosmic microwave background is still arriving from that direction. It travelled through space for billions of years before reaching our instruments. It crossed a growing universe, passed through eras when the first stars were born, galaxies formed, galaxy clusters gathered, planets appeared, life on Earth evolved, humans looked up at the sky, and then built instruments sensitive enough to recognize it. That light is not in a hurry. It does not need human eyes to notice it in order to exist. It keeps travelling, keeps arriving, and keeps carrying information from a time that is no longer here. The cosmic microwave background also changes the way we understand emptiness. If we choose a very dark region of the sky, far from bright stars, far from the Milky Way, and far from easily visible galaxies, we still cannot turn that region into absolute nothingness. The cosmic microwave background is still there. It is one of the reasons the idea of completely empty space becomes much harder to grasp than it first seems. A region may have no bright stars, it may not have a galaxy close enough for the eye or an ordinary telescope to see easily, but it still lies within the ancient background radiation that covers the universe. This image fits perfectly with the central message of the whole journey. Darkness is not nothing. In the case of the cosmic microwave background, darkness is where light has become too cold, too long in wavelength, and too faint for the human eye. It has not disappeared. It has only left the range of our vision. Like a voice so low that it falls beyond the hearing ability of the human ear, that light is still present. Our natural senses simply cannot catch it. Science, through microwave detectors, has brought that voice back into the field of human understanding, and once that voice is heard, it tells a very large story. It says the universe was once hotter, denser, and smoother than it is today. It says that the structures we see today did not appear from complete nothingness, but grew from very tiny fluctuations in the original density. It says that galaxies, stars, planets, and eventually we ourselves, all have a distant connection to subtle differences in the young universe. This does not remove the mystery of the universe. On the contrary, it gives that mystery a stronger foundation. We do not only feel that the universe is deep, we have data that shows how deep it is. When scientists create maps of the cosmic microwave background, they are not making beautiful pictures simply to look at. They are measuring extremely small differences in temperature coming from different directions. These differences are so tiny that without precise instruments, they would be swallowed by the nearly perfect uniformity. But inside those tiny differences, the universe keeps clues about the formation of structure. They are like the first wrinkles in the fabric of space and matter. After billions of years under the pull of gravity, those wrinkles grew into denser regions where galaxies and galaxy clusters could be born. We can picture this process with a gentle example. If you spread a very fine layer of flour across a table, and some places are just slightly thicker than others, the difference is almost unnoticeable at first. But if there is a mechanism that slowly causes grains of flour to slide toward the thicker regions, then over time those slightly thicker areas will become more obvious. In the universe, gravity plays the role of pulling matter toward regions with higher density. Of course, the real universe is much more complex. There is radiation, dark matter, ordinary matter, the expansion of space, and many other factors. But the main idea remains clear. Very tiny early differences can become very large structures after enough time. That makes the cosmic microwave background a bridge between two worlds, the early universe that was almost uniform and the modern universe filled with galaxies. When we look at it, we're not only asking where did this light come from, we're also asking why did the universe later take the shape it has today? It helps us understand that the darkness between the stars is not simply empty distance. It belongs to a larger history where light, matter and space evolved together. Every dark patch of the sky lies on the background of that story. Perhaps the thing that moves us most is the patience of this light. It is not light that was born yesterday. It is not light from a nearby lamp. It is light that has existed since before Earth formed, before the sun was born, before the Milky Way had the familiar shape it has now. It travelled through ages when no human eye could see it. It remained while generations of stars were born and died, and finally, in a small corner of one galaxy, a conscious species built machines that could measure it. There is something very gentle in this truth. The universe kept a record for a very long time, and science is the way we learn to read that record. But we need to stay accurate. The cosmic microwave background is not a curtain sitting at the edge of the universe like a physical wall. It is light from a distant time in the past, when every part of the observable universe emitted light after becoming transparent. Because light takes time to reach us, we see it as coming from a distant surface called the surface of last scattering. This can be confusing if we imagine it as a hard shell surrounding us. In reality, it is a limit of observation through light. Farther back than that time, the universe was still opaque to photons, so electromagnetic light cannot give us a direct image in the familiar way. In other words, the cosmic microwave background is a boundary of electromagnetic vision, not the final boundary of reality. Before it, in time, there were earlier stages, but to study those stages, science must rely on physical models, indirect traces, and in the future, perhaps other signals such as primordial gravitational waves if they are clearly detected. This makes the story even deeper. Darkness does not only contain ancient light, it also reminds us that some parts of cosmic history are even harder to reach, lying behind the curtain that light could not freely pass through at the very earliest times. Even so, what we have learned from the cosmic microwave background is enormous. It confirms that the universe was once hotter and denser. It shows that the early universe was very uniform but had tiny fluctuations. It helps measure cosmological parameters with high precision. It connects the dark sky today with the deep history of space. And most importantly for our journey, it proves that darkness is not absolute silence. A black sky can still contain light that has been stretched so far that the human eye can no longer see it. If we sit quietly and think about that, the night sky suddenly becomes different. The black regions no longer look like missing spots on a map. They are more like thin sheets of paper laid over an ancient text, where the writing still exists underneath, waiting for the right kind of light to appear. The cosmic microwave background is one of the oldest lines in that text. It does not speak through images of stars, but through the distribution of temperature. It does not speak through brilliant colours, but through extremely tiny differences between regions of the sky. It does not impress us with an explosion, but with an almost perfect uniformity after billions of years of travel. There is a beautiful paradox here. Darkness makes us feel that light is missing. But in this case, darkness is exactly where we discover the oldest light. That light does not compete for the attention of the naked eye. It does not appear as a blinding ray. It hides in the background, cold and even, like a breath from very far away. We need sensitive instruments to separate it from closer sources of noise, from radiation in our galaxy, and from signals from matter around us. But once it is separated, we realize it does not belong to one single object. It belongs to the history of the entire observable universe. This also explains why scientists have spent decades measuring the cosmic microwave background with greater and greater precision. Each better map is not just a more beautiful image. It is a deeper measurement of the past. Satellites and observatories have helped us see those small fluctuations more clearly, and from there test models of cosmology. When the data matches the model, we gain more confidence that we are understanding part of the story correctly. When there is an anomaly or a mismatch, we have a chance to learn something new. Science moves forward not by making darkness disappear, but by placing more precise questions inside the darkness. And if we return to the original feeling of a person standing under the night sky, all of this makes that moment wider. You look up and see a black patch. But behind that blackness is light that was born when the universe did not yet have mature galaxies. You look up and see quietness. But inside that quietness is data about the density of matter, the expansion of space, and the origin of cosmic structure. You look up and see the present, but in reality you are looking into the past. The night sky is not only the space above your head, it is an archive of time. So, darkness is not just a background that makes the stars stand out. It is a place where light that the human eye cannot see is still preserved and measured by science. Without the cosmic microwave background, our understanding of the early universe would be far poorer. We could still look at galaxies, stars, supernovae, and galaxy clusters, but we would be missing an extremely important background image of the young universe. This faint layer of light helps connect the present to the origin. It turns darkness from a meaningless distance into a path leading back to the first morning when light could freely travel far. Here, we can feel the main message of the whole story more clearly. Darkness in the universe is not completely empty, because it contains things that do not appear to the human eye. In the previous layer, we saw that darkness can be the limit of the senses. In this layer, we see that darkness also contains an ancient background of light. And that background light does not exist merely as a strange phenomenon. It is evidence, a map, a memory, and one of the keys that helps humans understand where the universe came from and how it developed. If one night you look into the black space between the stars, try to imagine that you are not looking into an empty gap. You're looking in a direction from which ancient light is still arriving. It has become weaker, colder, and longer in wavelength, but it has not vanished. It no longer belongs to the colours the human eye can sense, but it still belongs to the history of the universe. It is a gentle reminder that not everything important is bright. Some of the greatest evidence arrives in the faintest form. Some of the deepest light is hidden inside what we call darkness. And when we understand it that way, the night sky becomes a very different place. It does not only have bright stars in the foreground, it also has a distant background of memory behind them. Every direction carries part of the story of the young universe. Every dark region lies on a background of fossil light. Every black patch can be a window into the past, if we know how to use the right tools to read it. Darkness is not only space, darkness is an archive of ancient light. And inside that archive, the universe is still whispering about its own beginning. If the cosmic microwave background tells us that darkness still holds ancient light, then dark matter takes us into an even deeper layer of mystery. There are things that do not shine, do not reflect light like planets, and do not appear clearly in ordinary telescopes but can still be present because of their gravity. This is a very important lesson in astronomy. Something does not need to light up in order to be real. If it has mass, if it makes other objects move differently, if it bends the path of light, then it has left a trace. The first question is, if something does not shine, how do we know it exists? The answer is that we look at its effects. We do not see gravity with our eyes, but we see the moon orbiting Earth and we see Earth orbiting the sun. We do not see wind as an object, but we see leaves moving and the surface of water rippling. Dark matter is similar. We have not directly seen it through light, but we see many systems in the universe moving as if a large amount of extra mass is quietly there. One of the most famous clues comes from the way galaxies rotate. When astronomers measure the speed of stars and gas moving in many galaxies, they notice something strange. If we only count the mass of the visible bright parts, such as stars, glowing gas, and observable dust, gravity does not seem strong enough to explain the rotation speed in the outer regions of galaxies. Stars far from the centre still orbit faster than we would expect. This suggests that a galaxy is not only made of the bright disk of stars that our eyes can see. It may also sit inside a much larger, more invisible halo of dark matter that provides additional gravity. Imagine a city seen from far away at night. You see lights on the streets, inside houses, on bridges, and in buildings. If you only rely on those lights, you might think the city consists only of those bright points. But in reality, between the lights, there are roads, foundations, walls, water systems, electrical lines, and many structures that do not shine by themselves. A galaxy is similar. The stars are the most beautiful and easiest part to see, but they are not necessarily the whole story. Dark matter, as we currently understand it, may be the wider gravitational foundation, not shining, but helping the bright parts move in the way we observe. To be scientifically precise, dark matter is not ordinary black dust, and it is not ordinary cold gas that is simply hidden. Dust and gas still interact with light in ways we can measure. They can absorb light, emit light, dim light, or leave traces in a spectrum. Dark matter is called dark because so far it does not seem to interact with light the way ordinary matter does. It does not shine like stars. It does not reflect like planets. It does not create clear spectral lines like gas. But it has a gravitational effect, and gravity is the main path that allows us to recognize its presence. Galaxy clusters show the same thing. A galaxy cluster can contain hundreds or thousands of galaxies, along with hot gas and matter that does not shine. When scientists measure the motion of galaxies inside a cluster, they realize that the visible mass is not enough to explain why the cluster stays bound together. If there were only the stars and gas we can observe, many galaxy clusters would seem to lack enough gravity to hold their members together. There must be a much larger amount of mass. That mass does not appear directly through light, but it appears through motion. Here, darkness begins to have weight. It is no longer just the black colour between bright spots. It becomes a quiet gravitational field. Between galaxies in a cluster, where the human eye may imagine empty space, there may be a major component of mass that does not shine. It does not make the sky glow, but it pulls, it holds, it shapes. It keeps galaxies from simply drifting alone through space, and makes them part of a larger gravitational system. A very subtle way to detect dark matter is gravitational lensing. According to general relativity, mass curves spacetime, and light passing through curved spacetime will have its direction bent. So, a large galaxy cluster can act like a natural lens, distorting the images of more distant galaxies behind it. By measuring the amount of distortion, scientists can infer how much mass lies in the lensing region, including mass that does not shine. Imagine looking through a transparent but slightly curved piece of glass. You may not clearly see the glass itself, but the image behind it becomes distorted. From that distortion, you know something is sitting between you and the scene behind it. Gravitational lensing is similar, except that the glass here is the gravity of mass, and the distance can be as large as millions of light years. Dark matter does not need to shine on its own. It only needs to have gravity, and light passing through will carry the trace of that bending. A famous example is the Bullet Cluster, a system of two galaxy clusters that collided. When scientists observed it with many kinds of telescopes, they saw the cluster's hot gas in X-ray light, while the overall mass distribution was inferred through gravitational lensing. The remarkable point is that the region containing most of the mass inferred from lensing does not fully overlap with the region of ordinary hot gas. This is strong evidence that there is a component of matter unlike ordinary gas, one that interacts very little with ordinary matter during a collision, but still has gravity. In this case, darkness is no longer a vague idea. It leaves behind its own gravitational map. However, to stay scientifically accurate, we should not say that humans already know what kind of particle dark matter truly is. So far, the microscopic nature of dark matter remains an open question. Many hypotheses have been proposed, but no dark matter particle has been directly and firmly confirmed in the laboratory. What science knows very strongly is this. Many observations in the universe show that visible matter is not enough to explain all the gravity we see. The name dark matter is the way we refer to that missing component in the current model. This caution does not make the story less fascinating. On the contrary, it makes the story more truthful. We do not need to turn dark matter into something mystical. The reality itself is already deep enough. Most of the matter in the universe appears not to shine. It does not appear magnificently in astronomical images like stars and nebulae. But without it, many models of galaxies, galaxy clusters, and the large-scale structure of the universe would be missing a very important gravitational component. That invisible thing is helping explain why the visible part is arranged the way it is today. On a larger scale, dark matter is also connected to the cosmic web. When we map the universe on very large scales, galaxies are not spread evenly like sand scattered on a table. They gather into filaments, nodes, and clusters, surrounding enormous voids. The universe looks more like a giant web than an even empty space. In our current understanding, dark matter plays a major role in creating the gravitational framework for that web. Ordinary matter, meaning gas, stars, and galaxies, tends to gather along the gravitational regions shaped by dark matter. That is why people sometimes call dark matter the invisible skeleton of the universe. This is only a metaphor, but it is easy to understand. The skeleton inside the body is not the brightest part, and it is not the first thing we see, but it supports the overall shape. In a similar way, dark matter is not the part of the universe that appears most beautifully in photographs, but it may provide a gravitational framework where bright matter can gather. Galaxies are like glowing jewels resting on a much wider invisible structure. When we say that darkness in the universe is not completely empty, dark matter makes that statement much stronger. Because here, darkness does not only contain light that the human eye cannot see, it may also contain mass that light has not directly revealed. A region around a galaxy may look dark, but it may still lie inside a vast halo of dark matter. A galaxy cluster may look like separate bright points, but between them, there may be an invisible gravitational field holding the entire system together. A background region behind a galaxy cluster may appear distorted because its light has passed through a region of mass we cannot see directly. The universe, therefore, is not like a painting made only of bright parts. It is more like a huge stage in the dark. Stars are small lights, galaxies are glowing cities, nebulae are coloured clouds. But behind that scene, there are supports, cables, foundations, and structures that do not appear before our eyes. If we only look at the bright parts, we may think the lights are standing on their own. But when we observe motion and gravity, we see that the bright parts are sitting inside a much larger architecture. Dark matter does not only affect the present universe, it is also connected to the past formation of structure. In the early universe, very small density fluctuations gradually grew under the pull of gravity. Because dark matter does not interact strongly with light the way ordinary matter does, it could gather together and create a gravitational foundation for ordinary matter to fall into. Later, gas could cool, become denser, and form stars and galaxies. If the cosmic microwave background is the record of the earliest fluctuations, then dark matter is one of the ingredients that help those fluctuations grow into large structures after billions of years. This is a beautiful paradox. The light of galaxies may need darkness in order to be arranged. The spiral arms, star clusters, and glowing galaxies we see may be sitting on a gravitational background that does not shine. We often think of light as the main character, while darkness is only the backdrop. But in cosmology, that dark backdrop may be one of the reasons bright structures have a place to appear. We also need to distinguish dark matter from black holes. Both may seem dark in everyday language, but they are not the same thing. A black hole is a region of space-time with gravity so strong that inside the event horizon light cannot escape. Dark matter is different. It is inferred as a widely distributed component of matter that affects galaxies, galaxy clusters, and the cosmic web. Some hypotheses have considered the possibility that part of dark matter could be related to compact dark objects, such as primordial black holes, but that is not a confirmed conclusion for all dark matter. More accurately, dark matter is the name for the invisible gravitational component whose nature is still being studied. Dark matter is also different from dark energy. Dark matter helps explain additional gravity in galaxies, galaxy clusters, and large-scale structure. Dark energy is related to the accelerating expansion of the universe on very large scales. Both include the word dark, because they are not fully understood and do not shine in the ordinary way, but they are not the same thing. In this part, we're talking about dark matter, something that does not shine but has gravitational effects, something that gives darkness not only depth, but also mass. The reasoning behind dark matter is actually not unfamiliar. If a planet makes a star wobble slightly, we can infer that planet even if we do not see it directly. If one object pulls another object's orbit off course, we know hidden mass is present. If light passes through a region of space and bends, we can measure that bending to infer the distribution of mass. Science is not only about taking pictures of bright objects, science is about reading traces. Dark matter is one of the greatest examples of reading traces in the dark. So, darkness in the universe has its own solemn beauty. It is not like an abandoned empty room. It is more like a room with the lights turned off, but inside it are heavy objects that make the floor tilt slightly, change the path of light, and make objects move in ways that cannot be explained if the room were truly empty. If we only ask, "Do I see anything?" the answer may be no. But if we ask, "Is light being bent? Are galaxies rotating as predicted? Do galaxy clusters have enough visible mass?" then the answer begins to reveal a larger reality. Darkness does not speak through colour, it speaks through gravity. There is a very deep feeling that comes with this thought. What we see in the universe, all the stars, nebulae, planets, glowing dust and sparkling galaxies, is only the part of the universe that reveals itself through light. But the part that does not shine may play a very large role in organising structure. This does not make light less important. On the contrary, it makes the bright part more precious, because it's made of small signs that help us trace the invisible background behind it. A beautiful galaxy is not only beautiful because it shines, it is also beautiful because its motion suggests an architecture the human eye cannot see. When we look at an astronomical image, we're usually drawn to the brilliant regions, a spiral galaxy, a glowing nebula, a dense star cluster. But behind that beauty there is always a question. What holds it together? What guided its formation? What makes the light behind it bend? What makes the motion fail to match the amount of visible mass? Dark matter does not make the image brighter, but it makes the image deeper. It reminds us that the universe is not only what can appear in colour. The universe is also relationships of force, gravitational fields, and masses that do not show their form. If one day we could see with a sense that detected gravity the way our eyes detect light, the universe would look very different. Dark matter halos around galaxies might appear much larger than the bright disks of stars. Galaxy clusters might appear as enormous regions of mass, not just collections of bright points. The filaments of the cosmic web might stretch out like veins on a giant leaf. The dark spaces between galaxies would no longer be empty distances, but regions with their own gravitational structure. We do not have biological eyes like that, but through gravitational lensing, velocity measurements, cosmic simulations, and maps of mass distribution, science is slowly creating a kind of gravitational vision. The important thing is that evidence for dark matter does not come from only one single phenomenon. If there were only one unusual observation, we could question the data or the interpretation. But dark matter is supported by many different kinds of observations: galaxy rotation curves, motion inside galaxy clusters, gravitational lensing, the cosmic microwave background, and the formation of large-scale structure. These pieces come from different directions, but they all suggest that luminous matter is not enough to explain the universe as we see it. This is why dark matter has become a central part of modern cosmology. Of course, science continues to test it. Alternative ideas have been proposed, such as changing how we understand gravity on large scales. Asking those questions is necessary. But the model that includes dark matter still explains a very wide range of observational data. So, the most careful way to say it is this. According to current understanding, many lines of gravitational evidence suggest that the universe contains a non-luminous component of matter, one whose microscopic nature is still unknown, but whose role in cosmic structure is very large. That is a cautious statement, but it is also overwhelming. Think of a spiral galaxy in the night. The part we see is the disk of stars, where spiral arms spread out like rivers of light. But around that disk there may be a much larger halo of dark matter, not sparkling, not reflecting, not drawing a clear shape in ordinary photographs. The stars in the disk do not move only under the influence of the bright stars. They also move under the influence of the entire gravitational field around them. If we draw the galaxy only with light, the picture is beautiful but incomplete. If we also draw gravity, the invisible framework begins to appear. From there, we can look back at the night sky with a new feeling. When we look between the stars, we are not only looking into distance, we may be looking through dark matter halos, through regions of mass that do not shine, through the gravitational filaments of the cosmic web. Not every dark point contains the same density of dark matter. Not every black region is the same. but the entire universe cannot be understood if we only count what shines. The dark part is not secondary. It is part of the architecture. Perhaps this makes humans more humble. We often use light as a symbol of understanding. We say something becomes clear when we understand it, and unclear when we do not. But the universe is not limited by our language. It places a great deal of information inside things that do not shine. It lets a few galactic lights appear in the night, then forces us to infer the invisible gravitational background behind them. It shows us the prominent part, while the supporting part lies deep in darkness. That is the beauty of science. Science is not afraid of darkness. It steps into darkness with questions, data, telescopes, light spectra, lensing maps, simulations, and healthy skepticism. It does not turn darkness into myth, and it does not treat darkness as nothingness. It asks, if there is mass there, how much will light be bent? If there is extra gravity, how will a galaxy rotate? If dark matter exists, how will the large-scale structure of the universe form? If it does not exist, what model explains all the data better? Each of those questions makes darkness less silent. After the first 3 layers of this journey, we can look back and see the thread of the story more clearly. At first, darkness was the limit of the human eye. Then darkness appeared as a place that contains the ancient light of the early universe. Now, darkness may also contain invisible mass that pulls, bends, gathers and builds large-scale structure. These 3 layers all point to one message. Darkness in the universe is not a simple empty space. It is where reality continues to exist in ways that do not need to obey our vision. But ancient light and dark matter are only the first half of the story. The stranger part is this. Even if we imagine removing all the stars, all the dust, all the gas and all the galaxies from a region of space, modern science still does not rush to call what remains nothing in an absolute sense. Between galaxies, there are still extremely thin environments, wandering particles, hard-to-see streams of plasma, and deeper still, fundamental physical fields. The deeper we go into darkness, the more we see that the universe does not disappear. It only becomes more subtle, quieter, and harder to read. And now, after ancient light and dark matter, we step into a region that seems even emptier, the space between galaxies. When we look at a deep image of the universe, we often see galaxies like glowing islands scattered across a black ocean. Our eyes are drawn to bright galactic cores, soft spiral arms, and distant clusters of stars. As for the black space between them, we may easily think it is only empty distance. But modern astronomy shows that the space between galaxies is not a clean nothingness. It is an extremely thin environment, very hard to see, but real. If a galaxy is like a bright city in the night, then the space between galaxies is like the vast sky between those cities. From far away you only see clusters of lights. But between those clusters of lights there is still air, dust, water vapor, wind, radio waves, and many things the naked eye does not notice. The universe is similar, only on a far larger scale. Between 2 galaxies there may be millions of light years, and inside that immense distance there can still be gas, particles, plasma, weak magnetic fields, radiation, and very faint physical traces. Astronomers call this region the intergalactic medium. It is the matter that lies between galaxies, not concentrated into stars, planets, or clearly glowing nebulae. In that environment, there may be protons, electrons, scattered atoms, ions, and extremely thin clouds of gas. Some of the matter there is in the state of plasma, meaning electrons have been separated from atoms, creating charged particles. Some regions are very hot, even reaching millions of degrees, but because the particles are so sparse, they do not glow brightly like fire. It is hot but dim. It is real but almost invisible. This may sound counterintuitive. On Earth, when we hear that something is millions of degrees, we imagine blinding light, fire, explosions, or molten metal. But in intergalactic space, high temperature does not necessarily mean an easily visible glowing mass. Temperature tells us the average motion energy of particles. If the particles are extremely sparse, they can move very fast, but the total amount of light they emit can still be weak. It is like a few people running very fast inside a gigantic stadium. Each person has great speed, but the stadium as a whole still feels empty. The intergalactic medium is similar, rich in energy at the particle level, but extremely thin on large scales. Some popular descriptions from the United States National Aeronautics and Space Administration say that the intergalactic medium can be incredibly sparse, around 1 atom in each cubic foot in some easy-to-picture explanations. The actual density changes from region to region, but that number helps us feel the astonishing thinness of the space between galaxies. Compared with the air around us, it is almost a vacuum. But almost a vacuum does not mean nothing is there. This is a very important point. Science makes a clear distinction between extremely little and zero. If we take a small volume of space between galaxies, there may be only a few particles inside it, or even fewer depending on the region. But if we stretch that volume across millions of light years, the total amount of matter can become significant. The universe often misleads human intuition because its scale is so enormous. A tiny density spread across a gigantic volume can still become a meaningful amount of matter. So the dark region between galaxies may feel very empty in everyday terms, but it cannot be called absolute nothingness. We can imagine the intergalactic medium as a mist far too thin for the eye to see. If mist is thick, you see it immediately. But if there are only a few molecules scattered across a huge distance, the human eye cannot sense it. Even so, those molecules still exist. In the universe, the layer of matter between galaxies is thinner than any familiar mist. It does not block vision like fog, does not create a white colour, and does not give a feeling of moisture, but light passing through it can still leave traces. Those tiny traces show that darkness is not silent. One of the important ways to find this extremely thin matter is to read the spectrum of light from very distant objects, especially quasars. Quasars are extremely bright active galactic cores, often connected to matter falling into a supermassive black hole at the centre of a galaxy. The light from a quasar can travel across billions of light years before reaching us. Along the way, it passes through many thin layers of gas between galaxies. Those layers of gas do not appear as clear images, but they absorb certain wavelengths. When the light is split into a spectrum, astronomers see small absorption lines, like fine scratches on a band of light. These absorption lines are the signature of matter that is almost invisible. If a cloud of hydrogen gas lies between us and a distant quasar, it can remove part of the light at a wavelength that is characteristic of hydrogen. Because the universe is expanding, light from gas layers at different distances is redshifted by different amounts. So the spectrum of a quasar may contain many absorption lines, corresponding to many layers of gas along the path of the light. Some systems of lines like this are called the Lyman alpha forest, because they look like a forest of absorption marks related to hydrogen. What cannot be seen directly appears through the way it removes a very specific part of the light. Imagine shining a beam of white light through many very thin layers of glass. Each layer removes a little bit of its own colour. When the light reaches the end of the path, you analyse it and infer what layers it passed through. In the universe, those layers are not glass, but gas between galaxies. They are too thin to create a clear image, but real enough to write marks onto the light. So, darkness does not always need to shine in order to contain information. Sometimes, it speaks through the very precise absence of certain wavelengths. This kind of reading turns distant quasars into flashlights of the universe. Their light passes through dark space, meets gas, plasma, and matter around galaxies, and then carries the traces of that journey. When the light reaches a telescope, it is no longer only the original light from the source. It has become a record of what it encountered along the way. Thanks to this, scientists can recognize hydrogen, helium, ionized oxygen, carbon, silicon, and many other elements in an extremely thin environment. Elements heavier than hydrogen and helium are especially important, because they are often created in generations of stars and then spread outward through stellar winds, supernova explosions, and galactic activity. This makes the dark space between galaxies feel more alive. It does not only contain leftover primordial matter, it can also contain matter that once passed through the lives of stars. A galaxy is not a completely closed system. It can pull in gas from its surroundings to form stars, and then through stellar explosions or activity from its central black hole, it can blow gas and heavy elements outward. Matter enters a galaxy, becomes stars, is forged inside stars, and then some of it is pushed back into space. In that way, the dark environment around and between galaxies is part of the cosmic cycle of matter. Closer to a galaxy, scientists also talk about the circumgalactic medium, meaning the thin gas surrounding a galaxy before it gradually transitions into the wider intergalactic medium. If a galaxy is a glowing island, then the circumgalactic medium is like the water near the shore, where matter moves in and out. Farther away is the intergalactic ocean. Both are very faint, but very important. They show that galaxies do not live in isolation. A galaxy is not only the stars in its bright disk, it also has a broad region of influence where gas is pulled in, pushed out, heated, cooled, and then continues to take part in the history of star formation. Hot gas inside galaxy clusters is another clear example. When we look in visible light, we see galaxies as separate points or patches of brightness. But when we observe in X-ray light, a vast ocean of hot gas may appear between them. This gas is ordinary matter, but it is not inside stars. It fills the space between galaxies in the cluster and records the cluster's history of collision, merging, and gravity. Once again, the place the human eye imagines as a dark background may contain a large amount of matter. It is just matter that glows in a kind of light the human eye cannot see. Some ordinary matter in the universe may also exist as warm, hot, ionized, extremely thin gas in regions around galaxies or along the large filaments of the cosmic web. Because it is so thin, detecting it is very difficult. But through absorption lines in ultraviolet light or X-ray light, through weak emission, and through many indirect methods, scientists gradually trace it. This matters because not all ordinary matter is inside bright stars. A lot of matter may be spread thinly through darkness, not dazzling, but still part of the universe's matter budget. We usually pay attention to what is brightest. A bright star catches the eye. A brilliant galaxy makes us pause. A supernova explosion amazes us. But the universe does not operate only through brilliant events. It also operates through very thin layers of gas, faint streams of plasma, sparse particles, and processes that last for billions of years. The space between galaxies was not made to impress the human eye. It exists as a quiet material background, where light passes through, where elements are scattered, and where galaxies exchange matter with their surroundings. Inside that darkness, there are also wandering particles carrying high energy, cosmic rays. The word rays may make us think they are light, but most cosmic rays are matter particles, often protons or atomic nuclei, moving through space at very high speeds, with many particles moving close to the speed of light. They can come from the sun, from stellar explosions, from supernova remnants, from regions with strong magnetic fields, from environments around black holes, or from active galactic nuclei. Some particles have such extreme energy that their exact origin remains a research question. Cosmic rays make the idea of darkness feel more alive. If you look at a black patch of sky, you do not see any stream of particles. But high-energy particles are still moving through the solar system. Some are deflected or blocked by the sun's magnetic field, Earth's magnetic field, and the atmosphere. When a high-energy cosmic ray collides with the atmosphere, it can create a shower of secondary particles. We do not see it with the naked eye, but instruments can detect it. The darkness above our heads is not empty. It contains particles arriving from deep space, passing through like tiny messengers from violent events. It is worth noting that cosmic rays are among the few direct samples of matter from outside the solar system that we can measure. Light gives us a great deal of information, but light is not a heavy atomic piece of matter. Cosmic rays carry particles, energy, and sometimes clues about where they were accelerated. Because they are charged particles, their paths are bent by magnetic fields, so tracing their origin is not simple. But that very fact reminds us that dark space is not only an empty background, it contains magnetic fields, plasma, and processes that deflect the motion of particles. If the intergalactic medium is an extremely thin ocean, then cosmic rays are like high-energy fragments crossing that ocean. They do not make space light up like fireworks. They do not make the human eye notice their presence, but they prove that darkness is not completely still. Some particles have been accelerated in stellar explosions or extreme environments, then travelled through black space for a very long time. A tiny particle may have left the remnant of a dead star, been bent through the galaxy by magnetic fields, and finally left a signal in a detector near Earth. The space between galaxies is also connected to cosmic magnetic fields. Magnetic fields do not exist only around Earth or the Sun. Galaxies have magnetic fields. Galaxy clusters may have magnetic fields. Thin plasma in vast space may also be influenced by very weak magnetic fields. These fields are difficult to measure, but they matter because they affect charged particles, including cosmic rays. Once again, a dark region is not only a geometric distance, it has physical properties. It can bend, deflect, and record the motion of particles. Of course, we need to be balanced. Intergalactic space really is extremely thin. It is not like air, not like water, and not like any familiar environment around us. If we relied only on bodily sensation, we would not recognize any wind, fog, or flow there. But science does not measure the universe with bodily sensation. Science measures it with spectra, X-ray light, radio waves, high-energy particles, magnetic fields, and extremely tiny changes in signals. With those tools, the dark space begins to have texture. It is still very thin, but it is not meaningless. A very specific example is the light of a quasar passing through a layer of neutral hydrogen. That gas layer has no clear shape in a photograph. It is not a bright cloud. But in a spectrum, it removes part of the light at a characteristic wavelength. From the position and strength of the absorption line, astronomers can infer the composition, density, temperature, and motion of the gas. This is a very precise way of reading darkness. We do not see the gas cloud directly, but we see its signature on the light passing through it. Another example is hot gas in a galaxy cluster. If we only look at an optical image, we see separate galaxies. But when X-ray data is added, a vast hot environment between them appears. This gas shows that galaxies are not just bright objects sitting in nothingness, but members of a shared environment. On the scale of a cluster, the universe is more like a physical ecosystem than a collection of separate lamps. There is matter between the bright objects. There is an environment between the galactic islands. There is a story in the place the human eye mistakes for an empty background. From here, the message becomes clear. Cosmic darkness is not absolute silence. It contains extremely thin matter, plasma, absorption signatures, weak X-ray light, cosmic rays, magnetic fields, and the history of matter being exchanged between galaxies and their surroundings. None of this makes the space between galaxies dense like Earth's atmosphere. It is still an almost vacuum environment. But the word almost matters. Almost empty is not empty. Almost silent is not without signals. Imagine an astronomer observing a dark region between galaxies. In a visible light image, that place seems to contain nothing. But in the spectrum of a quasar behind it, there are absorption lines. In X-ray light, there may be signs of hot gas. In a cosmic simulation, that region may lie near a filament of matter in the cosmic web. In particle data, cosmic rays may be passing through. It is the same dark region, but each method opens a different layer. If we only look with the eye, we see absence. If we read it with science, we see an environment. That environment also helps us understand the long life of galaxies. A galaxy needs gas to form stars. Without a new supply of gas, star formation gradually decreases as gas is consumed or pushed out. The circumgalactic medium and the intergalactic medium can supply gas, receive gas back, or change that flow of matter. Winds from stellar explosions can push gas out of a galaxy. Activity from the supermassive black hole at the centre can heat gas or blow it far away. In the opposite direction, gas from the surrounding environment can fall into the galaxy and become raw material for new generations of stars. So, the dark space is not merely a background. It takes part in the evolution of galaxies. A galaxy, then, is not like a completely isolated island. It is more like a body breathing very slowly. It pulls gas in, forms stars, releases matter, enriched with heavy elements, and then interacts again with its surroundings. This cycle takes place over millions to billions of years. To the naked eye, everything seems still, but on cosmic timescales, gas still flows, plasma still heats up and cools down, particles still wander, and matter is still exchanged. Darkness is not motionless. It only moves at a rhythm too slow and too thin for our intuition. There is something very beautiful about the way matter is scattered between galaxies. Elements such as carbon, oxygen, silicon, and iron did not exist in large amounts at the beginning. They were created inside stars and in stellar explosions. When we detect traces of those elements in gas around or between galaxies, it means the products of past generations of stars have been carried out into vast space. The darkness between galaxies can contain the chemical ashes of stars that have died. It does not shine like a star, but it carries the ingredients of stars that once existed. Think of an oxygen atom in the intergalactic region. It may have once been created inside a massive star. That star lived quickly, died in a supernova explosion and pushed matter outward. Over time, some of that matter was blown out of its galaxy, mixed with the surrounding environment, and drifted through the space between galaxies. Billions of years later, light from a distant quasar passes through that region and is absorbed by an oxygen ion at certain wavelength. A scientist reads the spectrum and recognizes the trace. An almost invisible atom becomes a letter in the book of the universe. That is why the story of darkness is not only a story about the lack of light, it is a story about how even the thinnest things can become known. Science does not need a cloud to shine brightly in order to believe it exists. If it interacts with light in a consistent way, if it absorbs the right wavelength, emits the right signal, or affects its environment in the way a model predicts, then it becomes part of observable reality. Darkness does not hide everything completely. It only asks us to read more carefully. If dark matter shows us that darkness can have invisible gravity, then the intergalactic medium shows us that darkness can also contain ordinary matter in a hard-to-see form. This is an important difference. Dark matter has an unknown microscopic nature and does not seem to interact with light the way ordinary matter does. But gas and plasma between galaxies are more familiar kinds of matter. Protons, electrons, atoms, and ions. They're not mysterious in the same way. They're simply too thin, too hot, or too spread out to be easily seen. So darkness contains both the deeply mysterious and the very familiar, stretched thin across cosmic scales. This also helps us avoid a misunderstanding. When we say darkness is not empty, we do not mean every dark region is packed with matter. In reality, many regions of space are extremely thin. Compared with Earth, they are almost emptier than any natural environment we know. But the scientific question is not, is it as dense as air? The question is it truly zero? And the answer is no. There are particles, ions, fields, radiation, and traces. The difference between extremely thin and absolutely nothing is a very large difference. We can say the universe has many levels of emptiness. An empty room is still full of air. A vacuum chamber in a laboratory still contains some particles. The space between planets is much thinner. The space between stars is thinner still. The space between galaxies is even thinner. But at every level, empty is only a relative way of speaking. It describes sparsity, not absolute nothingness. When we use the word empty in daily life, we usually mean there are no objects. When we use it in cosmology, we must ask more clearly, empty of what kind of matter, at what density, on what scale, and with what measuring tool? That distinction makes the original question deeper. Darkness in the universe is not completely empty, because many things do not need to appear as stars. There is thin hydrogen gas between galaxies. There is hot plasma in galaxy clusters. There are ions absorbing background light. There are heavy elements blown out from galaxies. There are cosmic rays passing through. There are weak magnetic fields affecting charged particles. And all of this exists in an environment so thin that if we only looked with our eyes, we would think nothing was there. The more we think about it, the more we see that the universe is not only a place of large objects, it is also a place of small traces. A galaxy may weigh hundreds of billions of times the mass of the Sun, but a tiny absorption line in a spectrum can also reveal a cloud of gas between galaxies. A galaxy cluster may contain enormous mass, but a single X-ray photon can carry information about hot gas. A cosmic ray particle may be very small, but its energy can tell us about a violent acceleration process. The universe is vast, but we understand it through fine signals. Darkness is wide, but we read it through subtle traces, so we can see the black space between galaxies as an almost invisible ocean. That ocean has no water waves, no white foam, and no familiar sound. But it has extremely thin streams of matter. It has hotter regions, cooler regions, ionized regions, regions richer in heavy elements, regions near galaxies, and regions far from galaxies. It has charged particles deflected by magnetic fields. It has light from distant objects passing through and being marked. It has slow processes that connect the lives of galaxies to the wider space around them. What makes this part important is that it brings darkness closer to ordinary matter. After ancient light and dark matter, we may think darkness contains only things that are extremely strange. But the intergalactic medium reminds us that darkness also contains familiar particles, only in different states, thinner, hotter, more ionized, and more widely scattered. They are still protons, electrons, atoms, and ions. They are still matter connected to stars, galaxies, and chemical cycles. Something does not need to be completely mysterious to be astonishing. Sometimes the familiar becomes wondrous simply by being stretched across cosmic scales. Imagine a proton in the intergalactic region. It may exist in a space so wide that it hardly meets another particle for a very long time. But it is not nothing. It is part of the universe's matter budget. It contributes a tiny part to the environment through which light passes. It may belong to a stream of matter in the cosmic web. It may once have been near a galaxy, or someday in the far future it may be pulled into another structure. A tiny particle in the darkness is still a character in the larger story. From that point of view, cosmic darkness becomes a space with moving memory. Ancient light gives us the memory of the early universe. Dark matter gives us the invisible gravitational architecture. Gas and plasma between galaxies give us the memory of material cycles. Stars are born, stars die, galaxies blow gas outward, gas drifts into the wider environment, light passes through and records the trace. Cosmic rays give us the memory of high-energy events. All of them say the same thing. Darkness is not a pause, it is a connection. And so, when we look at the black regions between galactic islands, remember that the quietness is only the surface. Beneath it is a very sparse but real environment. There is gas too thin for the eye to see. There is hot plasma giving off weak signals in some environments. There are fine absorption lines in the spectra of distant light sources. There are cosmic rays rushing through at nearly the speed of light. There are weak magnetic fields bending the paths of charged particles. There are atoms and ions carrying the chemical traces of past generations of stars. The universe does not need to fill the space between galaxies with bright stars to prove that it is not empty. A little matter, spread across an enormous scale, is enough to turn darkness into an environment. At this point, the central message returns very clearly. Darkness in the universe is not completely empty. It is not empty at the level of light. Because there are forms of radiation the human eye cannot see, it is not empty at the level of gravity because dark matter leaves traces. And it is not empty at the level of ordinary matter either, because between galaxies there are still gas, plasma, ions, and wandering particles. The universe is not a few bright dots placed on a background of nothingness. It is a more continuous and more subtle system, where the bright and the dark both take part in a vast physical story. When we understand this, we no longer see the black regions between galaxies as blank spaces in the picture. They are more like the thin background layer of a piece of music. The main melody may not always be playing there, but without that background, the music would not feel complete. Galaxies shine, but between them there is an environment for light to pass through, for matter to be exchanged, for high-energy particles to wander, and for spectral traces to be written. Darkness is not absolute silence. It only speaks more softly than stars. It speaks through extremely low density, faint plasma, absorption lines, cosmic rays, and signals that science must patiently learn to hear. And after seeing that, we can go one layer deeper. If even the space between galaxies is not completely empty, then the next question becomes even more subtle. Suppose we keep removing more. Suppose there are no stars, no galaxies, no dust, no significant gas, and no wandering particles at all in an ideal region. Have we truly reached nothing then? Modern physics would answer very carefully. Because even a vacuum, understood through quantum physics, is not simply absolute nothingness. But before we reach that deeper layer, hold on to this image. Between the islands of galaxies lies an almost invisible ocean. The ocean is extremely thin, but real, and inside that almost unimaginable thinness, the universe is still quietly circulating. If the dark space between galaxies still contains gas, plasma, and wandering particles, then we can ask an even deeper question. What if we remove all of those things? Imagine an ideal region of space where there are no planets, no stars, no dust, no gas, no galaxies, no cosmic particles flying through, and not even a beam of light passing across it. If we could clean that region to an absolute level in our imagination, would what remains truly be nothing? In everyday life, we usually think of empty space as a place with no objects. An empty box is a box with nothing inside. An empty room is a room with no furniture. A dark region of the sky is a region without enough light for the eye to see. But modern physics forces us to be more careful. At a deeper level, empty does not necessarily mean absolute nothingness. A region may contain no ordinary matter particles, but that still does not mean it has no physical structure. It still has space, it still has time, it still has laws, and according to quantum field theory, it is still connected to fundamental fields. This is a very important point, and it is also a place where we need to speak slowly and precisely. In modern physics, elementary particles are not only understood as tiny marbles flying through an empty space. A deeper way to understand them is that quantum fields exist throughout space. Each kind of particle we observe can be viewed as an excitation of its corresponding field. To put it visually, a field is like a lake spread out wide, while a particle is like a measurable ripple on the surface of that lake. When there is no clear ripple, the lake does not turn into nothingness. It is still the lake, still with its ground state. The vacuum in quantum physics is similar. The vacuum is not an empty box in the everyday sense. It is the lowest energy state of quantum fields. Lowest does not mean it has no properties at all. It means the system has no real particles that can be counted by an ordinary detector, but the fields still have a ground state. This is a major difference between everyday intuition and modern physics. Intuition says that if we remove all objects, nothing is left. Physics says that if we remove all real particles, we still have the vacuum state of the fields. From here, we understand why scientists say that space is never completely empty in an absolute sense. This does not mean that there are dense secret clouds of matter hidden in the darkness. It also does not mean that we can extract unlimited energy from empty space. Statements like that are very easy to misunderstand. The more accurate meaning is this. In the modern quantum model, the vacuum is a physical state, not the total absence of everything. It can have quantum fluctuations, field correlations, and effects that may become measurable under special conditions. You may have heard the idea that, in a vacuum, pairs of virtual particles and antiparticles constantly appear and disappear. That statement can help people imagine the idea, but we have to use it very carefully. Virtual particles are not the same as real particles flying out of the darkness and disappearing like tiny grains of dust. In quantum field theory, virtual particles are often a mathematical tool used to calculate interactions between fields and real particles. If we describe this too simply, we can turn a technical concept into something almost mythological. A safer way to say it is this. The quantum vacuum has fluctuations and field correlations, and descriptions using virtual particles are a useful calculation method in many problems. This does not make the story less wondrous. On the contrary, it makes it deeper. The strange part is not imagining tiny particles popping in and out like fireworks. The strange part is this. Even the state we call the emptiest is not the same as absolute silence in mathematics and physics. The fields still exist, the laws still operate, the ground state still has properties. Darkness, if we follow it all the way down, is not only a place where light is missing, it is a place where the foundations of physics are still quietly present. One famous example often mentioned when discussing the quantum vacuum is the Casimir effect. Imagine two uncharged metal plates placed extremely close together in a vacuum, so close that the distance between them is on a tiny scale. Under the right conditions, a very weak but measurable attractive force can appear between the two plates. The common description connects this phenomenon to changes in the quantum fluctuations of the electromagnetic field between the plates compared with outside them. More simply, the presence of the two metal plates changes which field states can exist in the space between them, and that difference creates a very small force. The important thing is that the Casimir effect does not prove that the vacuum is a storehouse of energy that can be easily exploited. It is also not evidence for vague ideas that nothing creates everything in the everyday sense. It is a subtle quantum phenomenon that appears under special conditions at very small distances and is described by quantum field theory. That subtlety is exactly what deserves respect. It shows that empty space is not always like a flat, meaningless background. When we place very specific boundary conditions into it, such as two conducting surfaces very close together, we can measure the influence of the quantum structure of the field. Imagine a room so quiet that you think there is no sound at all. But with an extremely sensitive device, you might still detect tiny vibrations in the walls, the air, and the matter around you. The quantum vacuum is not like a room filled with air, but this image helps us understand one thing. Absolute silence is very hard to achieve in nature. At the quantum level, the background of reality is not a dead blank sheet of paper. It is more like a minimal state, with no real particles in the ordinary sense, but still with properties described by physical equations. However, we also need to avoid going too far. We should not say that the quantum vacuum is an ocean of matter in the sense that we can scoop it out and weigh it like water. We should not say that real particles are constantly being created from nothingness and disappearing in a way we could directly observe with our eyes. We should not say that darkness is a mysterious energy source waiting for humans to exploit. Those descriptions sound exciting, but they can distort the science. Quantum physics is already strange enough without exaggeration. The most accurate point is this: the vacuum is the ground state of fields, and that state is not the same as absolute nothingness. When we bring this idea back to the universe, the original question becomes much deeper. Darkness in the universe is not completely empty, not only because it contains ancient light, dark matter, thin gas, or cosmic rays. Even if we imagine removing everything that could be called matter and radiation, modern physics still does not allow us to simply call what remains nothing, because in the language of quantum fields, space is still tied to fields and their vacuum states. That is a very deep kind of presence, unlike any object in everyday life. We can imagine the universe as a stage. The stars are bright performers, galaxies are grand productions, dust and gas are the mist, the props, and the material of the scenes. Dark matter is the gravitational framework that is not clearly visible but shapes the arrangement, and the quantum vacuum is like the stage floor itself, along with its silent rules. Even when no actor is standing on the stage does not disappear. It still has structure. It still determines what kinds of motion can happen. It is still where the laws of physics are written. Saying this does not mean the vacuum is an object. It is not a liquid, not a gas, and not a layer of invisible dust. It is a state of fields. This is why everyday language is always difficult here. When we say field, many people think of a piece of land. When we say vacuum energy, many people think of a container filled with energy. When we say fluctuation, many people imagine visible water waves. But in physics, these words have more technical meanings. They describe quantities, states, and correlations that can be calculated, not simple material images. That is why, if we want to stay scientifically accurate, we should speak with humility. The quantum vacuum is one of the deepest and most difficult concepts in modern physics. It works very well in many calculations in particle physics and field theory, but when connected with gravity and cosmology, it leads to questions that have not been fully solved. One major question is the relationship between vacuum energy and the cosmological constant, or what is often discussed in modern cosmology in the context of dark energy. Simple calculations from quantum field theory and the observed value of cosmic acceleration do not match in an easy way. This is one of the deepest problems in theoretical physics, but we do not need to go too far into that problem to understand the message of the video. What we need to keep is this: the vacuum is not ordinary nothingness. It is not simply a dead empty space between objects. It is the ground state of quantum fields, and in some circumstances the properties of that ground state can have measurable consequences. If darkness is where the human eye does not see light, then the quantum vacuum is where we learn that even when light and matter are removed from the picture, the physical background has not vanished. Let us return to the image of an ideal region of space that has been cleaned out. No stars, no dust, no gas, no plasma, no significant radiation, no wandering particles. Our intuition wants to say, finally, we have reached emptiness. But physics will ask further questions. Do quantum fields still exist? Does space-time still exist? Do the laws still exist? Is the ground state of the field still a physical thing to describe? If the answer is yes, then this is not absolute nothingness. It is a physical state that is very poor in real particles but not poor in meaning. This difference is very subtle. Absolute nothingness, if we use that term in a philosophical sense, means nothing at all. No space, no time, no laws, no fields, no possibility of measurement. A physical vacuum is different. It still exists within space and time. It is still described by equations. It can still respond when there are boundary conditions, external fields, gravity, or objects placed within it. So, the vacuum of physics is not the nothing of philosophy. This is a very important distinction that helps us avoid misunderstanding popular statements about the universe being born from nothing or particles being born from empty space. In our story, that distinction helps clarify the central theme. Cosmic darkness is not completely empty, but that does not mean darkness is a mystical thing with a will of its own or a strange source of energy. It means that at many different levels, what we call empty must always be defined. Empty to the human eye is not empty to microwaves. Empty to visible light is not empty to gravity. Empty of bright objects is not empty of thin gas. And empty of real particles is not necessarily empty of quantum fields. There is a very calm beauty in this chain of thought. At first, we look at the night sky and see blackness. Then we learn that this blackness may contain the cosmic microwave background. We learn that it may contain dark matter. We learn that between galaxies there are still gas, plasma, ions, and cosmic rays. And now, we learn that even the idea of an ideal empty space is not simple. The deeper we go, the less the universe looks like an empty room, and the more it resembles music with many layers of background. There is a layer of sound we can hear. There is a layer too low or too high for the ear. There is a layer that only appears when we use sensitive enough equipment. And there is a layer embedded in the structure of the music itself. We can use another image. Imagine a lake late at night. There are no boats on the surface, no falling leaves, and no clear moonlight. You say the lake is empty. But the water still has molecules, still has heat, still has tiny fluctuations, still has surface tension, and still obeys laws. If you do not see waves, the lake does not become nothingness. Of course, the quantum vacuum is not water, and quantum fields are not ordinary fluids, but the image helps us understand the general idea. The absence of obvious objects does not mean the absence of the physical background. With the quantum vacuum, that physical background cannot be fully pictured by the eye. It is understood through mathematics, experiments, subtle effects, and the consistency of theory. In the quantum world, quantities such as energy, fields, and states do not behave the way classical intuition expects. A system can be in its lowest energy state and still not be a perfect zero in every respect. Vacuum fluctuations are not the motion of tiny objects in the everyday sense, but properties of the quantum state of a field. This may sound difficult, but it reflects a larger truth. At its deepest foundation, the universe was not built to be easy to imagine through everyday experience. When physicists talk about quantum fields, they are not only talking about things located somewhere in a laboratory. Fields are a fundamental way to describe particles and interactions at very small scales. The electromagnetic field is connected to photons. The electron field is connected to electrons. Other fields are connected to other particles in the standard model of particle physics. When a field has the right excitation, we observe a particle. When there is no real particle excitation, the field still has its ground state. So the vacuum is not a place where fields are absent. It is where fields are in their lowest state. This is directly connected to darkness. A dark region may emit no visible light. An ideal vacuum region may contain no real particles. But neither one is nothing in the simple sense. In astronomical darkness, signals may lie beyond the senses. In the quantum vacuum, properties may lie beyond the image of objects. Both teach the same lesson. Reality does not have to appear as bright things before the human eye. Some levels of existence are recognized through effects, equations, measurements, and consistency between theory and observation. Here, we should also speak carefully about vacuum energy. In quantum physics, the ground state of a field can be associated with zero-point energy, meaning the lowest energy level that cannot be reduced further in the quantum description. But when this idea is brought into cosmology and gravity, everything becomes very difficult. Vacuum energy may be connected to the way space expands, but the exact relationship between vacuum energy and field theory and the dark energy we observe remains a major unsolved problem. So we should not confidently say that vacuum fluctuations are dark energy as a finished conclusion. The more accurate way to say it is this. This is a deep area of research where quantum physics and cosmology meet, but many questions remain open. That caution makes the story more trustworthy. Science does not always give a final answer. Sometimes science is strongest when it clearly states what is known, what is not known, and where the boundary lies between them. We know that the vacuum in quantum field theory is not absolute nothingness. We know that some effects, such as the Casimir effect, show that the vacuum state of a field can be connected to measurable phenomena under special conditions. We know that the universe is expanding at an accelerating rate, and dark energy is the name for the component or phenomenon related to that acceleration in the cosmological model. But we do not yet fully know the deepest nature of dark energy or how to completely solve the vacuum energy problem in gravity. When you hear this, the story may feel more difficult, but let it slow down. The main point is not that you have to understand all the mathematics of quantum field theory. The main point is to change the way we look. Dark space is not like a dead background. Even when bright objects are absent, it is still a place where laws operate. Even when there are no real particles, it can still be described as the ground state of fields. Even when we call it a vacuum, the word vacuum in physics is richer in meaning than the word empty in daily life. There is a very special feeling when we think about this at night. You look up at a black region of the sky. At the first level, you know your eyes do not see all forms of light. At the second level, you know there is ancient light in the form of microwaves. At the third level, you know dark matter may be creating a gravitational framework. At the fourth level, you know that between galaxies there are still gas and particles. And at an even deeper level, you know that even the idea of emptiness is no longer simple. The universe does not seem to have any layer as poor and empty as our first intuition suggests. The quieter it becomes, the more it asks us to listen with finer tools. Imagine an astronomer in an observatory seeing nothing in a region of the sky with the naked eye. That person does not rush to say there is nothing there. Instead, that person asks, is there a radio signal? Is there infrared? Is there X-ray light? Is there absorption in the spectrum? Is there gravitational lensing? Is there cosmic microwave background radiation? And if every material signal were somehow removed, the physicist would ask one more question. How is the vacuum state of the fields described? The question does not stop at blackness. Blackness is only the beginning of an investigation. That is why darkness in the universe is so compelling. It does not give us an answer immediately. It forces us to pass through many layers. It teaches us that reality may be present through light, gravity, spectra, particles, fields, and extremely small effects. It makes us humble before what we have not yet seen. And it also gives us a quiet kind of pride because humans, from a small planet, have learned how to ask questions all the way down to the ground state of space. But once again, we need to avoid misunderstanding. The quantum vacuum does not mean that anything can naturally and permanently appear from nothing. The conservation laws of energy, momentum, electric charge, and many other quantities remain very important. Descriptions involving virtual particles are not permission to imagine real matter being created for free again and again. In experiments, creating real particles usually requires real energy, such as in high-energy particle collisions or in extremely strong fields. The quantum vacuum is a precise concept in physics, not a magic phrase that lets us ignore the laws. This makes our message even clearer. Darkness is not empty, but it is also not chaotic in an arbitrary sense. It is not a place where anything happens for no reason. It is a place where the laws of physics remain very strict. Quantum fields are not mystical chaos. Vacuum fluctuations are not magic. The Casimir effect is not free energy. The deeper the universe becomes, the more it demands precision, and that precision is what makes its beauty last longer than any exaggeration. When we say the vacuum is a ground state, we're talking about a structured quietness. It is like a rest in a piece of music. A rest is not the destruction of music. It is part of the music placed within rhythm, staff, and rules. The vacuum is not the destruction of physics either. It is a state that physics can still describe. There are no real particles, but that does not mean there are no fields. There is no visible light, but that does not mean there is no theoretical background. There are no objects, but that does not mean there is no possibility of interaction if conditions change. That image helps us connect with the larger rhythm of the video. Darkness in the universe is like an enormous musical rest. At first, we think a rest means there is no music, but when we listen carefully, we realize the rest gives the music depth. It creates room for other sounds to appear. It holds the rhythm. It gives us a sense of structure. Darkness is the same. It is not an empty gap in the music of the universe. It is the background where ancient light passes through, where dark matter keeps the gravitational rhythm, where thin gas circulates, and where quantum fields still have their ground state. We could say that the quantum vacuum is the layer that makes the question of emptiness the hardest. With dust, gas, and plasma, we are still talking about ordinary matter. With dark matter, we're talking about invisible mass, but still a component of observational cosmology. With the cosmic microwave background, we are talking about ancient light. But with the quantum vacuum, we are asking about the deepest foundation of what we call empty space. And the answer is not a simple sentence. It is a shift from thinking in terms of objects to thinking in terms of fields, from everyday intuition to modern physics, from are there objects or not to what is the state of the fields. If you stand under a dark sky and think this way, you will no longer feel that you are looking only at absence. You are looking at a layer of reality where the absence of objects still does not mean the absence of physics. Scientists spent many generations developing language precise enough for this idea. And even today, the vacuum remains a deep area of research, connected to particle physics, cosmology, quantum gravity, dark energy, and many unfinished questions. But precisely because it is unfinished, it reminds us that darkness is not a period. It is an ellipsis. Notice how the story expands step by step. When we only look with our eyes, darkness is blackness. When we look with many wavelengths, darkness is hidden light. When we look through gravity, darkness has hidden mass. When we read spectra, darkness has gas and elements. When we measure particles, darkness has cosmic rays. When we enter quantum field theory, darkness is also connected to the ground state of fields. Each layer does not erase the previous one. It adds to it. Darkness is not one single answer. It is a set of many levels of hard-to-see presence, and if we need to reduce it to one simple image, we can say this. The universe is not like a box with a few glowing marbles sitting in empty space. The universe is more like a living physical background, where light, matter, fields, gravity, and space-time together create reality. Stars are the easy part to see, galaxies are the brilliant part, but even the dark spaces between them cannot be dismissed as meaningless. At the deepest layer described by modern physics, empty space is still a state, not an absolute negation. Perhaps this is why the question, why is darkness in the universe not completely empty, is so powerful. It begins as a question for the human eye, but ends as a question for all of physics. It begins with the night sky, but leads us to the cosmic microwave background, dark matter, the intergalactic medium, and the quantum vacuum. It begins with the feeling that there is nothing there, and gradually shows that there are things there that do not resemble familiar objects. And that journey turns darkness from a colour into a deep concept. So, if we remove all the stars from a region of space, it may still contain gas. If we remove all the gas, it may still contain radiation. If we remove all the radiation, it may still lie within a gravitational field. If we imagine removing all real particles, it still does not necessarily become absolute nothingness, because quantum fields still have a ground state in the physical description. Every time we try to move closer to nothing, science asks us what we mean by nothing. And the more tightly we define it, the more we see that nothing in daily life is very different from vacuum in physics. This is not wordplay. It is the core of how science works. A familiar word can become insufficient when we step into the scale of the universe or the quantum level. Dark is not only the lack of visible light. Empty is not only the lack of objects. Vacuum is not only an empty box. Each concept must be clarified through measurement and theory. When we do that, we do not take away the poetry of the universe. We make it deeper, because the beauty now lies not only in the image, but also in the precision of understanding. And finally, the layer of the quantum vacuum brings us to a very peaceful feeling. Peaceful not because there is nothing. Peaceful because everything has receded into the deepest background. There is no dazzling star, no brilliant galaxy, no easily visible gas cloud. But the fields remain the foundation of physics. The laws are still present. Description is still possible. Darkness at this level is like a room with no voices, but still with architecture, still with a floor, walls, space and rules for how sound would echo if one day a noise appeared. So, darkness is not only where light is missing, it is the stage background where the laws of physics still operate. It may have no obvious objects, but it is not the erasure of reality. It may be quiet, but it is not meaningless. It may feel empty to intuition, but it is not empty in the way modern physics describes it. And when we understand that, we see that the universe does not need to blaze with light in order to be profound. Sometimes, the deepest part of the universe lies exactly where it seems most silent. After passing through the quantum vacuum, we can step far back and look at the universe on its largest scales. At that distance, we no longer see individual stars, and we no longer see each galaxy as a lonely island. Instead, a wider picture appears. Galaxies are not spread evenly like sand across a table. They gather into filaments, walls, clusters and superclusters, while between them are enormous empty regions. The universe is not like a black curtain with a few random points of light. It is more like a vast web, where light clings to the veins of matter, and darkness lies between those veins like wide chambers of space. That large-scale structure is called the cosmic web. If we imagine the universe as a gigantic spider web, then the web's filaments are places where matter is more concentrated, places where galaxies often appear. The intersections are the densest regions, where large galaxy clusters can form, and the dark spaces between the filaments are cosmic voids. These voids can be tens to hundreds of millions of light years across. They look like the blank parts of the map, but in reality they are an essential part of that map. The important point is that cosmic voids are not absolute nothingness. They are regions with far fewer galaxies and much less matter than the surrounding filaments and clusters. Inside them, there may still be some faint galaxies, extremely thin gas, dark matter at lower density, background radiation, high-energy particles, and physical fields. So, the word empty in cosmology is a relative concept. It means thinner, more sparse, and less rich in bright structure. It does not mean that absolutely nothing is there. The cosmic web is deeply connected to dark matter. According to the current cosmological model, dark matter plays an important role in creating the gravitational framework for large-scale structure. In the early universe, matter was not distributed with perfect uniformity. There were tiny density fluctuations, where one place was slightly denser than another. The denser regions had slightly stronger gravity, pulling more matter toward themselves. Over billions of years, those tiny differences were amplified. Dark matter gathered into vast gravitational regions, and ordinary matter, gas, stars and galaxies tended to follow that gravitational framework. So galaxies did not form on a meaningless empty background. They formed inside a network that gravity had gradually shaped. Places where matter gathered became filaments, walls, and clusters. Places where matter moved away, or gathered less, became voids. Darkness on the largest scales is not outside the history of the universe. It is a result of that very history. If we only look at the bright galaxies, we see only half the picture. If we also look at the voids, we begin to see the true shape of the network. We can imagine this like a piece of lace. A piece of lace is not made only of threads. It is also made of the open spaces between the threads. Without the open spaces, we would only have a solid piece of fabric. Without voids, the cosmic web would not appear as a shaped structure. The dark regions make the bright filaments stand out. The places with fewer galaxies help us recognize where matter has gathered. So darkness is not the leftover part of the universe. It helps define the architecture of the universe. Voids are also tools for testing our understanding. If our models of dark matter, gravity, expansion, and the universe's initial conditions are correct, then computer simulations should be able to create a cosmic web with clusters, filaments, walls, and voids that closely match what we observe. Each void is not only a region with fewer galaxies, it is a test. It asks our model, did matter gather in the right way? Did gravity work as predicted? How did expansion affect large-scale structure? And does the rate of galaxy cluster formation match the data? Imagine a map of a city seen from above at night. The bright regions show where there are houses, major roads, and neighborhoods, but the dark regions matter too. They may be lakes, parks, mountains, open land, or places where fewer people live. If you only look at the bright regions, you know where the city is. But if you look at both the bright and dark regions, you understand the structure of the city more fully. The universe is similar. Galaxies are the lights. Voids are the dark regions. Together they create the real map. Voids also show how matter has moved over time. In the cosmic web, matter tends to gather toward higher density regions under the pull of gravity. Regions that were slightly thinner at first gradually lost matter to the surrounding filaments and clusters. So, as the universe ages, the contrast between dense regions and sparse regions increases. Clusters become clearer. Filaments grow longer and more prominent. Voids become larger within the large-scale structure. Darkness, therefore, does not stand still. It also takes part in the growth of the cosmic map. Saying that dark regions help the universe grow does not mean voids create stars or galaxies like factories. The main idea is this: dark, sparse, low-matter regions are the necessary contrast that gives structure its shape. If galaxies and galaxy clusters are dark ink strokes, then voids are the paper beneath them. If matter gathering is the story of gravity, then voids are the trace showing that matter has gathered somewhere else. Darkness does not compete with light. It gives light a place within a larger structure. From the cosmic web, we move to an even bigger story: the expansion of space. Space is not a fixed stage where galaxies simply fly through. On very large scales, the space between galaxies itself is expanding. This does not mean Earth, the solar system, or a galaxy is being stretched like rubber. Systems already bound by gravity or other forces keep their structure. But between galaxy clusters that are very far apart, where they are not strongly bound, distance can increase with the general expansion of the universe. We know this through the light of distant galaxies. When light travels through expanding space, its wavelength is stretched. This phenomenon is called cosmological redshift. The farther away a galaxy is, the more strongly its light is usually redshifted, giving us a clue about the expansion of the universe. So the dark regions between galaxy clusters are not merely distances. They are places where the expansion of space is expressed on large scales. For a long time, scientists once thought the expansion of the universe might be slowing down because the gravity of matter was pulling back against it. That sounds very reasonable. If everything's moving away from everything else, gravity should tend to slow that separation. But observations of very distant Type 1a supernovae revealed a surprising result. The expansion of the universe is not only continuing, it is accelerating. To name the unknown cause connected to this phenomenon, scientists use the concept of dark energy. Dark energy is a concept that needs to be discussed very carefully. It is not dark matter. Dark matter helps explain additional gravity in galaxies, galaxy clusters, and the cosmic web. Dark energy is connected to the accelerating expansion of the universe on very large scales. Both contain the word dark because they are not fully understood and do not shine like stars, but they are not the same thing. If dark matter is like an invisible gravitational framework that helps matter gather, then dark energy is connected to the tendency for distances between faraway regions of the universe to increase faster over time. In the standard cosmological model, dark energy is often described by the cosmological constant, a component with energy density that is almost constant throughout space. As the universe expands, the density of matter decreases because matter becomes spread through a larger volume. But if dark energy has a property that remains almost constant throughout space, its relative influence becomes more important in the later universe. This helps explain why the expansion of the universe can accelerate. Even so, the true nature of dark energy remains an open question. It may be connected to the cosmological constant, it may be connected to vacuum energy, or it may require a deeper understanding of gravity and space. This is where darkness returns with its largest meaning. The enormous voids between structures are not only places with fewer galaxies, they are places where we feel more clearly the role of space itself. Galaxy clusters are like islands held together by gravity, but the distance between those islands, if it is large enough and not strongly bound, can continue to grow with the general expansion. In the very distant future, If accelerated expansion continues as current models predict, many galaxies outside our local region will move farther and farther away, and their light will become harder and harder to reach us. The future sky may become far more isolated. This thought is both scientific and quietly sad. Darkness does not only preserve the past through the cosmic microwave background, it may also signal the future through expansion. The dark spaces between galaxy clusters are not just a black background. They are places where distance is growing. They are places where the future map of the universe is being written, not through explosions, not through brilliant light, but through the very slow fading apart of enormous structures. Of course, science today is still testing the nature of dark energy. We know the universe is expanding at an accelerating rate. We call the unknown cause dark energy, but we still do not know for certain what it is at the deepest level. Large surveys are measuring the positions of millions of galaxies and quasars to reconstruct the history of expansion and the formation of structure. Each better measurement helps us understand whether dark energy truly behaves like the cosmological constant, or whether it changes over time. The most accurate way to say it is this: dark energy is one of the greatest mysteries in modern cosmology, and the answer is still being tested with data. What makes dark energy special is that it does not gather into stars, planets, or galaxies the way matter does. It is connected to the background of space on large scales. So, the wider and more sparse a region is, the more it helps us think about the role of space in the evolution of the universe. Space is not just a box that contains everything. In general relativity and modern cosmology, the geometry and dynamics of space are part of the story. The universe does not only have matter moving through space itself has a history. Picture a sheet of fabric with dust particles resting on it. If the fabric is stretched, the dust particles move farther apart, even if each particle does not run across the fabric by itself. Cosmic space is not a real fabric in the material sense, but this image helps us feel the idea of expansion. Distant galaxies are not simply flying through a fixed stage. The distance between large regions of space is growing. Where gravity is strong enough, structures hold together, but on the larger scales, the background of space continues to expand. Cosmic voids may be places where that expansion becomes especially clear in the structure. As matter gathers into filaments and clusters, voids become wider and more distinct. As space expands, distances between large structures increase. As dark energy becomes dominant in the later universe, the formation of new structures on very large scales may be slowed down because accelerated expansion makes it harder for distant matter to gather together. So, dark regions are not only products of the past, they're also connected to the limits of what may form in the future. In everyday life, an empty space is often a place waiting to be filled. An empty chair waits for someone to sit in it. An empty room waits for furniture. A blank page waits for writing. But cosmic voids are not necessarily places waiting to be filled. In a universe with accelerating expansion, many distances may continue to increase. Regions with little matter may remain regions with little matter, and may even become more isolated from the surrounding structures. Space is not waiting for humans to fill it. It has its own history, laws, and dynamics. So, cosmic structure is the result of two great tendencies. Gravity pulls matter together, forming galaxies, galaxy clusters, filaments, and the cosmic web. Expansion increases distances on large scales. Dark matter helps the framework of structure form. Dark energy is connected to accelerated expansion in the later universe. Voids sit between those two stories. They are both the trace of matter gathering somewhere else, and the regions where the expansion of space becomes clearer. There is a very quiet beauty in this. Stars tell their story through light. Galaxies tell their story through shape and motion. Dark matter tells its story through gravity. Intergalactic gas tells its story through absorption lines and weak emission. The quantum vacuum tells its story through the ground state of fields. And voids and dark energy tell their story through distance. Not every story in the universe is told through objects. Some stories are told through moving apart, through sparsity, and through the growing silence between islands of light. Imagine drifting inside a cosmic void. Around you, there is no dense starry sky like we often imagine. The nearest galaxies may be extremely far away, only faint points if you have powerful enough instruments. The place may feel so lonely that it is hard to picture, but from a scientific view, you are not outside the universe. You're inside a very real part of it. You're still within the background of cosmic microwave radiation. There is still a little scattered matter. There are still physical fields. Space is still taking part in the general expansion. That dark region is not where the story ends. It is a quiet chapter of the story. In dense regions, gravity writes the story by pulling matter together. In sparse regions, the lack of matter also writes the story by allowing distance to open wider. Both are necessary. If we only study places with many galaxies, we learn how matter gathers. If we also study voids, we learn how unevenly the universe is distributed, how expansion affects it, and whether our models describe low-density regions correctly. The darkest regions, therefore, are not ignored. They become natural laboratories of cosmology. We can see voids as pauses in the music of the universe. A piece of music is not made only of high notes and loud sounds. It needs pauses for rhythm to have meaning. The cosmic web is the same. Galaxy clusters are the strong notes. Galaxy filaments are the long melody. Voids are the wide pauses. But a pause is not the absence of music. It is part of the structure of music. Darkness is not the absence of the universe. It is part of how the universe is written. At this point, we can connect the whole journey. At first, darkness was only the place where the human eye did not receive enough visible light. Then we learned that darkness contains the cosmic microwave background, the fossil light from when the universe was young. Then we met dark matter, which does not shine but leaves gravitational traces. Then we passed through gas, plasma, ions, and cosmic rays between galaxies. Then we reached the quantum vacuum, where empty no longer resembles everyday nothingness. And now, on the larger scales, we see that darkness is also the shape of structure, the distance of expansion, and the place where dark energy raises questions about the fate of the universe. Perhaps this is what makes the story feel both vast and close. It is vast because it speaks of billions of light years, the cosmic web, voids, and accelerated expansion. It is close because it touches a very human feeling, the feeling of standing before darkness and wondering whether anything is there. Science's answer is not simple, but it is beautiful. Yes. There are many things there, in many different senses. There is unseen light. There is mass that does not shine. There is gas too thin for the eye to see. There are high-energy particles. There is the ground state of fields. There are voids shaping the network. There is the expansion of space itself. And here, we realize something very strange. Throughout this entire journey, darkness has never been a side character. It does not merely sit between the stars. It holds the first light, hides invisible matter, contains thin gas, carries high-energy particles, expresses quantum fields, and expands with space itself. Darkness is not what remains after the universe finishes telling its story through light. Darkness is where the story continues in another language. If we look back at the night sky after understanding this, the blackness above us no longer feels the same. It is no longer an empty curtain. It is more like a map too deep for the naked eye to read completely. Where we see few stars, there may be ancient radiation. Where we see a black background, there may be a halo of dark matter. Where we imagine distance, there may be thin gas and spectral traces. Where we imagine a vacuum, quantum physics still speaks of the ground state of fields. And where we imagine a great emptiness, cosmology sees voids, the cosmic web, and the history of expansion. Darkness does not stand outside the universe. Darkness is part of how the universe is built, expands, and evolves. It is the background where light appears. It is the distance that gives structure its shape. It is the sparse region that allows matter to gather into filaments. It is the stage where the laws of physics continue to operate. It is the future expanding between galaxy clusters. When we ask why darkness in the universe is not completely empty, we're not only asking about matter, we're asking how reality exists when it does not shine before human eyes. We could say that the universe teaches us a very deep lesson through its own darkness. What is bright easily catches our attention, but what is dark forces us to think. Light gives us images, darkness gives us questions, light gives us direct beauty, darkness gives us depth, and when science enters that depth, it does not find a meaningless void. It finds history, structure, gravity, plasma, quantum fields, expansion, and mysteries that remain open. So the darkest regions are not where we should stop looking. They are where we should look in more ways. With microwave light, we see the past. With gravitational lensing, we see invisible mass. With spectroscopy, we see thin gas. With X-ray light, we see hot plasma. With particle detectors, we see high-energy messengers. With cosmology, we see voids and expansion. With quantum physics, we see that the vacuum is not simple nothingness. Each way of looking opens one part of the darkness, and each part says the same thing. Not seeing something with the eye does not mean it does not exist. Hold on to one image. The universe is like a glowing web suspended in deep black space. The bright points are galaxies. The faint glowing lines are filaments of matter. The great dark regions are voids. But the dark regions are not the forgotten parts. Inside that very darkness, ancient light is still passing through. Dark matter is still forming the framework. Thin gas is still leaving absorption lines. High-energy particles are still wandering. Quantum fields still have their ground state, and space is still expanding. The universe is not vast only because it has many stars. The universe is also vast because even the darkness between the stars contains layers of meaning so deep that humans have needed centuries just to begin reading them. Tonight, we have travelled through a very quiet journey, but also a very deep one. From a question that seems simple at first, why is darkness in the universe not completely empty? We have seen that darkness is not the end of reality. It is only the place where reality no longer appears in a way the human eye can easily recognise. When you look up at the night sky, you may see black spaces between the stars, but now those black spaces are no longer a simple absence. Inside them, there may be the ancient light of the cosmic microwave background radiation, a cold and faint trace from the time when the universe was still very young. Inside them, there may be dark matter, something that does not shine and does not appear like the stars but still leaves its trace through gravity, through the motion of galaxies, and through the way light bends. Inside them, there may be extremely thin gas, hot plasma, scattered ions, and fine absorption lines in the spectra of distant light sources. Inside them, there may be cosmic rays, high-energy particles quietly moving through space at nearly the speed of light. And deeper still, even the vacuum is not absolute nothingness, but the ground state of quantum fields, as modern physics describes it. On the larger scales, darkness also helps us see the shape of the universe. Galaxies gather into filaments, walls, and clusters, while between them lie enormous voids. Those voids are not leftover parts of the universe. They are part of the cosmic web, part of expansion, and part of the way space evolves over time. So perhaps the greatest value of this journey is a new way of seeing. Darkness is not only the lack of light. Darkness is where history, structure, energy, gravity, thin matter, physical fields, and mysteries are preserved, while science continues to decode them. And now, as everything around you becomes quieter, let that thought drift slowly. Out there, darkness is not empty. It is holding the oldest memories of the universe, the quietest motions, and some of the deepest questions human beings have ever asked. Sleep well. May your mind become light, as if it is drifting among distant stars. Thank you for travelling with Drift into Quiet Knowing. And when we meet again, we will continue listening to the secrets the universe only whispers in the dark.